Hall sensor experiment. In this Hall sensor experiment, the semiconductor device it detects the magnetic field. So Hall sensor device have a three terminals. See, we have a three terminals here: positive power supply and negative or grounded second terminal, and third terminal is output terminal. See in the diagram, Hall sensor device. So three terminals we have. So first terminal is positive power supply, DC power supply, and negative is or grounded. Both positive and negative it will supply the voltage. And the third terminal is output voltage, and second terminal is common for both input voltage and output voltage. Operator in this experiment: 9-volt battery, magnet, Hall sensor, battery switch, breadboard, potentiometer, and multimeter. In the potentiometer, we have a three terminals. In the three terminal, first terminal is positive power supply input, and second terminal is negative. This negative is both input and output is common, and the third terminal is output positive power supply. So you will connect positive power supply and negative to the battery, and we will supply the voltage battery to the potentiometer. Using the potentiometer knob, we are changing the input or supplying voltage, and that voltage is passing through the output terminal number 3 and 2. Circuit diagram for Hall sensor experiment. See potentiometer part, three terminals: positive, negative or grounded, and output positive. See positive power supply first terminal and second terminal negative or grounded, we are connected to the input power supply 9-volt battery, and that 9-volt battery we are supplying required voltage in the potentiometer using the potentiometer knob. That voltage is passing through the output potentiometer wire terminal 3 and 2. So what's the required bias voltage in the experiment? That required bias voltage you are passing through the Hall sensor, and using this Hall sensor terminal number 3 and second, you are measuring output voltage in the same multimeter. In the Hall sensor experiment, you are applying magnetic field. See this magnetic field perpendicular to the charge carrier density, charge carriers. See the Hall sensor, it carries the charges. You are applying magnetic field perpendicular to the charge carriers. So here transverse electric field is develops. The transverse electric field gives the Hall voltage. In that Hall voltage, directly proportional to the applied magnetic field B and applied current high, and inversely proportional to the charge carrier density and thickness of the sample. Then Hall voltage VH becomes VH is equals to high B divided by NE into D. Here VH is the Hall voltage, high is the applied current, constant current or constant bias voltage, or B is the applied magnetic field, and divided by NE. NE is the charge carrier density and D is the thickness of the sample. Circuit connection in the experiment. So first Hall sensor 3-terminal device, we will connect to the 3-terminal pin. See here, 3 terminal pins we are connected Hall sensor, and magnet connect to the movable guide. We are connecting magnet to the movable guide and Hall sensor to be fixed guide. On 3 terminals Hall sensor, so first we are set the bias voltage. In the bias voltage wires, power supply 2 wires of the bias voltage, we are connecting in the breadboard. First positive and negative or grounded wire, connect, and take battery connect to the switch. See now this positive power supply 2 wires, positive power supply wire and negative wire, we are supplying bias voltage in these 2 wires, and output wire we have Hall voltage, we are measuring Hall voltage in the output wire. We will connect this side. Negative is common for both input input voltage and output voltage. Now we will measure the first bias voltage. We are setting bias voltage as the constant voltage. Take multimeter. Circuit is DC. In the DC circuit, we are measuring DC voltage. Multimeter positive power, positive wire, you can connect voltage, and negative is common, grounded. So in the range of DC voltage, we will set range is 20, and take positive and negative wire. Positive wire we will connect to the positive wire, we will connect to the positive of the power supply, and negative wire we will connect negative of the power supply. Battery we will connect here. Using the potentiometer knob, we will set bias voltage. See, first bias voltage is 3. It is constant bias voltage. We will set 3. Yeah, now bias voltage is 3. In this bias voltage, you are measuring Hall voltage. So you are using same multimeter. Multimeter positive wire disconnect in the bias voltage and connect to the Hall sensor output wire. Only positive wire you can connect, and negative is common for both input and output. Now apply the magnetic field in a different distance. Hall sensor, it will detect the magnetic field strength. So first, in a closed distance, measure the distance between magnet to Hall sensor. Change the distance between Hall sensor to magnet. Take scale. You can take the reference point. Initial reference point is 0. So now I am considering this is 0. Now change the magnet 0.5 increment. See the voltmeter. See the voltmeter. See, voltage is changes. Increasing the distance, voltage is decreases. So now we can say that magnetic field is decreases, increasing the distance. So Hall sensor is detects the strength of the magnetic field and Hall voltage. After the constant bias voltage 3, remove the Hall voltage positive multimeter wire, and you can connect to the positive power supply of the bias voltage or input voltage, and change the bias voltage. Next bias voltage is 4. Using the multimeter, this potentiometer knob, we will keep 4. Yeah, we will set constant 4. And in this constant bias voltage, we are measuring Hall voltage. Change the multimeter positive wire, you can disconnect and connect to the Hall sensor wire output terminal. Change the distance. You can start from the closed distance. First closed distance we will consider this is 0. 0 to 0.5 increment we will start this. 0.5, 1 till 5 centimeter we will change the distance and tabulate the Hall voltage. Increasing the distance, that Hall voltage is decreases. So we can say that Hall voltage is directly proportional to the strength of the magnetic field. Here VH is directly proportional to the applied current and magnetic field, and universally proportional to the charge carrier density and thickness of the sample. After tabulating the Hall voltage, we will plot the graph VH, Hall voltage versus distance. In a 3 different bias voltage, we will plot the graph. We are getting 3 different curves. See, bias voltage 3, 4, 5. In a 3 different bias voltage, we will plotting the graph Hall voltage versus distance. Increasing the distance, Hall voltage is decreases. Result and conclusion in this experiment: increasing the distance, Hall voltage is decreases. So we can say that to detect the magnetic field strength or Hall voltage in different distances using the Hall sensor in 3 different constant bias voltages.